welcome you to my lecture today. And of course, the focus today is going to be on bootstrap regression. Give me 1 second. I'm actually going to share my lecture slide. Okay, so I need every one of you to actually confirm if you've seen my lecture slide. Okay, I'll give you 1 second. I think okay, so you can see that now, right? Okay, so like I said, the focus today is going to be on bootstrap regression. And of course, on the outline, I'm basically going to walk you through essence of bootstrapping. Then from there, we're going to go into bootstrap regression, how it works. Then I'm actually going to mention, what is the difference between this type of regression and other statistical regression we've talked about in this class, like data method and, the weighted least square and so on like that. Okay, so what I'm actually showing you here is basically, how the bootstrap statistics work. Okay, I got a population now. Okay, and traditionally, we normally choose sample size, right? The sample size is actually a fractional part of the population, and of course, we choose the sample in a way to ensure the central limit theorem hold. Okay, even though if the population distribution we are actually choosing sample from is not normal. Of course, there's a way we can actually make the sampling distribution, of the statistic from that, okay, to be normal. Okay, now the idea behind bootstrap statistics is just like, okay, I choose a sample from a population, and of course, the sample that I choose from the population, I can actually boot that, okay, in such a way that I can boot that several times. Okay, for instance, if I initially choose a sample size of 20, okay, from a population, of course, we got a technique in statistics that can actually be used to do what I call a sampling within a sample. And we can actually do that like so many times. By do that 1,000 times, on each occasion, I'm actually still going to have 20. Okay, and at the end of the day, the distribution of that, okay, the idea is just like we basically want the distribution of that to follow normal distribution. Of course, the implication of having normal distribution for inference, right? For meaningful inference, of course, that is the reason why we need that. Okay, so you know in regression analysis, of course, just like what I used to say in class, we find ourselves in a world, where we basically want to characterize relationship among variables. And you know what, the conventional regression, I mean, the linear regression we normally use, of course, have assumptions, you know that, right? And what if these assumptions are not met? Okay, but the particular assumption I really want to talk about is the normality of residual, because when the residual behaves well, when the no error behave like a residual, when the error behave like a white noise, we're basically going to say, oh, okay, the error actually followed normal distribution, and implication of error follow normal distribution is that the regression coefficient is also going to be assumed to follow normal distribution. So which is actually the basis, the foundation of statistical inference. So which means inferences, and accurate standard errors for parameters, okay, and mean functions, require either normality of regression errors, or if there is a situation where there's no normality, or according to central limit theorem, if we have a large sample size, the normality can actually be guaranteed. So what I'm trying to talk about for us to have what I call a meaningful inference. Okay, when I say meaningful inference to be taken, on the linear regression, of course, we expect the error to follow normal distribution, and for the error to follow normal distribution, it actually implies the distribution of the regression coefficient is also going to follow normal distribution, because it is when they do that whatever hypothesis testing that we may want to conduct on the regression parameter is basically going to be reliable, or even if you want to construct a confidence interval. In fact, what I actually want everyone to have in mind is I need a standard error, of course, to construct a confidence interval or to conduct an hypothesis testing. And of course, we're actually going to have a reasonable standard error if the assumptions of normality of residual hold. And you know what? In small samples, without normality, of course, the standard inference method can actually be misleading. And this is where we need, you know, another method and technique beyond linear regression. And one of them is bootstrap regression. Of course, before now, I've walked everyone through another technique that can be used that we call the weighted least squared when I was discussing stabilizing the variance. Okay, so the bootstrap regression, is just a method of random sampling with replacement. Okay, and of course, it has enabled us, to stabilize the variance of regression coefficient, and in a way, we're basically going to have a robust standard error for regression coefficient in place in case we want to conduct an inference. And what I mean by inference is I may want to construct a confidence interval around my regression parameter, or I basically want to conduct an hypothesis. Now, in order to showcase, how, the bootstrap regression work, basically going to start using the idea of, the simple linear regression. Okay, so in a simple linear regression now, I basically, you know, I want to simulate a data set for response variable Y, and I'm also want to simulate data set for predictor variable X, of course, and I want 1,000 observations, and you know what, I'm setting a seed here. Of course, I basically want to use our software. I set a seed here. I put 2022. When you also put 2022, you're actually going to get the same set of data like me, because when you are simulating from distribution, of course, if you don't set seed, we're actually going to have, simulate our different data set. Okay, setting the seed and putting, if you put the same number that I put, you're basically gonna have the same data set. So here I'm actually telling how I need 1,000 observation. Of course, the 1,000 observation is very good enough, to be qualified, the normal distribution, right? So I simulate my X from normal distribution, as you can see that. And of course, I also simulate my response variable. And the response variable is actually a linear combination. It should be a function of the predictor, as you can see. And of course, this code is I'm actually naming my data set to be population.data. And of course, the data dot frame here is just for to simulate the bivariate data X and Y. Okay, that is actually going to come in terms of column. Okay, so take a look at that. Okay, so of course, the way I constructed my response variable, I did that by adding noise to the explanatory variable. You can see right here, the explanatory variable that I also call predictor. Okay, you know, I added noise to that, and adding noise to that is just more or less just going to tell you all just trying to make our data set contaminated. You get what I mean? Okay, so this is the population data. Now the next thing I actually want to do is taking a sample size of 20. Of course, if you go by central limit theorem, right? 20 is less than 30. The threshold for a large sample as given by central limit theorem is at least 30. You get that, right? Okay, so but right now, if I decide to take something less than 20, I mean less than 30, like a 20 observation from this population data, of course, this is the code right here. Of course, in statistical analysis, what we always do is basically to take a sample, as we don't study the entire element in a target population. You get what I mean? Okay, so this is a code, the R code, to actually take a sample randomly from the population of data. Now, what I'm going to do next is basically let us now exploit the simple regression model. We're going to exploit the simple regression model on the population data. We actually going to observe, what we have in terms of regression coefficients, the standard error, along with other, stuff. Then we're also going to do the same for sample uh, data, and we're also going to observe the same. Now, I wanted to take a look at what I have now. Okay, I'm using population data. I'm using 1,000 data, right? And I regress Y on X, and this is my estimate of the intercept. This is the slope, and as you can see here, we got the R squared. Okay, so take a look at that, and of course we're told here that our X is significant. Okay, of course I'm actually going to refer to this guy, okay, as the true values. Okay, they are the true values of the parameters. Of course I'm using the entire um data. You get what I mean? Okay, of course when we use the entire data in the population, of course we're going to be very close to the truth. Okay, so we're going to call that the true values of parameter. Okay, now what I'm basically going to do now is I'm going to show you the effect of taking sample. Okay, now instead of using the 1,000 data set, and I decided to use 20. And of course, don't forget the 20 was actually taken randomly from the population data. We basically want to see result now. Okay, so take a look at this guy now. So I've used the sample data of 20. Okay, and there's something I wanted to pay attention to, the estimate of the regression constant here that I'm actually going to call the intercept is bias. Take a look at that. Okay, so that is actually bias, even though the slope is kind of very close, right? The slope is very close, but the intercept is bias. Okay, and because of that, the reason for that is we may not be able to trust the standard error here. Okay, and we may not be able to trust them because the reason why that happened is because we are working with a sample, small sample. And of course I mentioned the other time, in small sample we may not be able to trust the standard error of our regression coefficient, and of course we actually need a way to stabilize that. Of course, the solution to this problem is, okay, if you are ready to go into the population and take more sample, there's no problem. But most of the time, don't forget when we are conducting our research, we are limited by budget. Okay, we're not only looking for efficiency, but we're looking for a way, to reduce, the cost. Okay, so and that is the reason why, actually here, Bootstrap is actually going to help us out if we still want to work with a 20. Okay, we still want to work with 20. So what is going to happen now? So I'm basically going to show you. Another thing I wanted to take note. So, here, look at the standard error here of the coefficients. Okay, compared to here. Okay, the standard error of the coefficient when you are using the population data is lesser than the other one when you use sample data. That was why I told you the other time, when assumptions is violated in a linear regression, is basically going to affect the variances of the regression of parameters. So that is exactly what you're saying now. Okay, that's exactly what you're seeing now. Okay, so like I said, the way out, okay, the way out is basically using the bootstrap approach. Okay, so using the oh no, what I'm just trying to show you here is just the plot of the two models. But let me go to the bootstrap. Okay, the idea behind the bootstrap is more or less like, okay, can we if we resample the data with replacement, okay, and estimate the coefficient, how extreme, that will be. Okay, I can decide to do 1,000 trials, okay, and resample with replacement the 20 observations in our sample size and actually runs that, and let's see what's going to happen. Okay, now this is the code, of course, if you want to do that in R. As you can see here, it's like I'm going into that very sample 20, they have 20 observation 1,000 times. Okay, I got nothing to do with the population. Don't forget, when we're doing the bootstrap, we don't go back to the population anymore. We basically want to boot bootstrap want to boot our what we the data set we have in the sample. That's why you see the code, our code here actually centered on the sample data. Okay, so what I'm actually going to have, I'm actually going to have 1,000 pairs of regression parameters. Okay, which I wanted to take note. So when you take a look at what I have here now, okay, those are the regression coefficients that actually came out from the bootstrapping. So which means I got 1,000 intercept. Okay, basically going to find the mean or the median of that, and of course I'm actually going to have 1,000 regression slope, and of course we're going to have rate that. Okay, we can also calculate the bias between this and what the linear regression actually gave. Now, what I'm actually showcasing here, as you can see, between the result that we got from sample and the one we got from the bootstrap, you can see the one from the bootstrap is the one that is actually very close, okay, to the population regression parameters. And that is the reason why we're actually seeing a bootstrap regression as a way out. If you don't want to spend more, going into the population, increasing your sample size. Okay, so take a look at that. Of course, the bootstrap is actually working. Okay, so the next thing I'm actually going to talk about is the confidence interval associated with that. For the population, 95% confidence. Now, you basically see for the intercept and the slope, for the population, the sample, and the bootstrap, that's exactly what I put here. And of course, this is a graph. Okay, so this is actually showing, the graph of the bootstrap, the population, the sample, and as I said before, that of the bootstrap is actually very close. And of course, I'm actually recommending, the bootstrap when the sample size is very small. Okay, you know how small it should be before you can actually consider using the bootstrap idea. Okay, so I'm gonna go into another, uh, you know, give me 1 second, another material now on this bootstrap where the one I demonstrated the other time, I simulated, right? I'm actually going to give you the idea when I'm using the true data now, okay? This is when I'm using real data, okay? Here I'm looking at the effect of weight, age, and gender on cholesterol, total cholesterol, right? And of course, here I'm actually want to use the old data set of the participant, right? Which means I actually using the multiple linear regression here, right? Okay, so when you take a look at this is a coding how to do that. And when I do the summary, okay, I have this result. Okay, I wanted to pay attention now, okay, to this result. Okay, I'm actually going to be focusing on age. Okay, if you really want to measure how age, okay, actually contribute to cholesterol, okay, when you put into consideration other covariates like weight and gender, okay, you actually put all those variable at constant because they also influence, they influence, the total cholesterol level. Okay, this is using multiple linear regression. And of course, the assumption in the multiple linear regression here is just that, okay, you know what, um, the error follow normal distribution. And when error follow normal distribution, we expect the regression coefficient. What I mean that by regression coefficient, we expect this intercept, the slope associated with weight, age, and gender to actually follow normal distribution. That is exactly what I mean. Okay, so this is a confidence interval for each of that. As you can see, if I'm focusing on age, the age is significant here, right? The p-value is very, very small, and the confidence interval agree with that because the if you look at this interval does not include zero, which actually means our age is significant, of course, to the total cholesterol level. Okay, so when I decide to take a sample of 20, okay, maybe I don't want to use all the observation here. I think the observation here is going to be 341. This is 397. By the time you had 1, 2, 3, 4, so we have um, 401 observation, right? If I decided not to use that and I decide to use 20, and I call that D5, and that very 20 was actually, sample from the 401 that I mentioned the other time. And I actually conduct another multiple linear regression based on the sample now. As you can see, I got a different result. The age initially was actually significant, right? If I go back, the age was significant initially when I use population data, but right now it's no longer significant. And not only that, the confidence interval for age now included zero because it's from negative to positive. Okay, I wanted to take note of that. But when I resample, when I do bootstrapping, okay, now this is the code. If you want to do bootstrapping, you can load, library car in your house studio. Of course, what I want to do now, I'm still going to be using 20, okay, my D5, but the only difference is just like I'm actually going to boot, right? I'm going to boot like here, I'm booting 10,000 times, okay? Now, booting 10,000 times, it actually means I'm actually going to have 10,000 intercept, the 10,000 slope associated with age, the 10,000 slope associated with gender. Okay, and at the end of the day, I'm actually going to I'm going to report the average of all of that. Okay, now I wanted to look at the confidence interval generated. Okay, the confidence interval, generated. The confidence interval generated here, compared to what we have before the age, from negative. Okay, this is actually also telling us that the age, okay, is not significant, okay, just like what that of the sample was actually telling us. But there's something I wanted to say in summary. Now, when I use 403, initially we have 403, but due to missingness, we actually remove two. That was why I was calling 401 the other time. Okay, two observations were deleted due to missingness. Okay, now uh, I wanted to compare result now. Okay, using the for audio data set, the full data set. Okay, age estimate was 0.66, and of course we call that true regression. Okay, and this actually give us the confidence interval, right? Now when I use 20, okay, data set, the age actually gave us 0.76, and of course from negative is 0.5 to that. And when I boot, okay, when we boot now, okay, we have a 0.76, even though we still have from negative to that. Now, of course, in the sample data and in Bootstrap data, age is not significant, but there's something I wanted to pay attention to. Okay, when you compare the range here, okay, and when you compare the range here, you're basically going to see that we have, when you compare the range here, okay, and when you compare the range here, you're basically going to see that we have more confidence with the bootstrap, okay, because the interval here is very close. You know, when you have a smaller range of interval, you know, it's actually come with a lot of confidence. Okay, if you take a look at what I have here compared to, you know, negative is 0.551 to 2 is very wide compared to negative is 0.385 to 1.802. And that was why I said here above, we see that the bootstrap confidence interval for the age coefficient in the bootstrap model is narrower. Okay, narrower means more confidence, as you know, that's what I'm just showing you, than, you know, that in the limit model. However, it did not get narrow enough to tell us the effect of age on the total cholesterol is negative, okay, zero or positive. So to tell you that, you know, Bootstrap is not actually going to solve the problem entirely, but in a way, it's basically going to close the gap in the interval, which is more or less very close to the truth. Okay, so this is where I'm actually you know, gonna start today on the Bootstrap. And of course, this is the histogram. You know, for those of you that care about what the histogram is going to be at the end of the day, to see whether one can achieve normality with the Bootstrap. Of course, we're going to have different form of that. You know, you're going to have the normal density, you're going to have for Kenneth density, you're going to have for BCA, and the observed value. So take a look at that. Okay, so like I said, this is where I'm actually going to stop today. They said they want to ask question. Of course, you can send me a message if you don't want to ask now. So that is you know, something on Bootstrap regression, and make sure you stay safe and have a lovely day.